There's really nothing new at this point about the kinetic theory of gases. We've already made use of many of these ideas, and those ideas are that gases are mainly empty space, which is to say that the volume of the molecules is small compared to the volume that they occupy. The gas molecules are in constant chaotic motion, and we can take a look down here at the model and see what we mean by that. So if you look at the gases, you have all sorts of different velocities and movements, and there's really no way to describe them individually. So when we talk about gases, we're really talking about the average properties in most cases. The collisions of the gas particles are elastic, so one particle can transfer energy to another one, but there's no energy that's lost. That's the meaning of the word elastic. And finally, that the pressure is caused by the collision of the molecules with the walls of the container. So this is the theory, and this is what we would call the kinetic molecular theory of an ideal gas. So one of the ideas that we make use of is that the kinetic energy, or the average kinetic energy of translational motion, which is usually just called the kinetic energy, is dependent on temperature and directly related to temperature. And if you have two gases, like we have represented here, and they're at the same temperature, then they must have the same kinetic energy. So that's an idea that is useful to us because it covers a lot of situations with gases, because anytime you have a mixture of gases, they're going to be at the same temperature. So there are two words that we use to talk about the movement of gases. One is diffusion, which we use to describe when you have gases that are moving from a high concentration to a low concentration. But this would be like something diffusing through the air. And that's a fairly slow process because there are a lot of molecules in the way. On the other hand, we talk about effusion, and effusion is when you have gas molecules that go through a tiny opening, a pinhole or a pore. And usually when we are talking about gases and their movement, we're talking about effusion. So there are really two factors that affect the rate of effusion. One is the pressure of the gases. Clearly, the higher the pressure, the faster the rate of effusion. And the other thing is the relative speed of the particles, so how fast they're going. The equation that we use to describe this rate of effusion is that the rate of the effusion of one gas, we can call that B, relative or divided by the rate of effusion of the other gas, A, is inversely related to the square root of their masses. Another way to say the same thing is the lighter the gas is, the faster it goes. So they have the same kinetic energy, but that energy will affect a lighter gas more in terms of its velocity than it will a heavier gas. So this diagram sort of represents what we were talking about. So if you have two gases, one which is at a high mass and the other which is at a relatively low mass, then the one with the higher mass is going to effuse more slowly, because if the particles are moving more slowly, then the likelihood of them going through this small opening is going to be less. On the other hand, when the molecules move faster, they're going to hit every surface more frequently, but they will certainly go through the opening at a faster rate or more frequent rate than the heavier molecules. Okay, in this problem we're going to be using Graham's law, but we're given the information about the rate in a slightly different form. So let's see if we can understand this. So we can say that the rate is equal to the moles of, we'll say, argon, and the argon takes 32 seconds in order to get to a pressure of 12.5 millimeters of mercury. And then the rate for the other gas, this would be the rate of X, is going to be moles of X, and this one takes 48 seconds to achieve the same number of moles. Okay. Now, the other thing we know is since both of the gases get to the same pressure, then the number of moles of argon equals the number of moles of the unknown gas. So we can set this up. Let me see. I'll do it over here. So we can say, and the argon goes faster. So if we put the argon, so we can say in argon, which is 32 seconds, so that's the rate for the argon, over the rate for x, which is nx divided by 48 seconds. Okay, so that's going to equal the mass of x over the mass of argon, which is, we'll just go ahead and say 40, all to the square root. Okay, so when we, let me just kind of point, so when we take this and divide it by the one over here, what we're going to end up with is we're going to have 48 over 32, and that's going to be equal to mx, so the molar mass of x over 40, and then it's going to be the square root of all that. Okay, so we can square both sides. So I'm just going to need a little bit more room. Let me see if I can move all this. I can. So I'm going to move all this up here like so. All right. So 48 divided by 32 is 1.5, and then if we square both sides, so I'm going to square 1.5. So 1.5 squared is 2.25, and that's going to be equal to the molar mass of x divided by the molar mass of argon. So I just need to solve for mx. So I just multiply 40 times 2.25, and I get pretty close to 90, so about 90 grams per mole. You can use this idea, this principle, to separate any sorts of gases that you have. So it was actually used to purify, or it is used to purify uranium. So if you have the two isotopes of uranium, so you have uranium-238 and 235, then what you can do is convert those both into gases. So that's uranium hexafluoride, uranium-238 hexafluoride, and uranium-235 hexafluoride, and then if you have those two gases together, then the lighter gas, which is the uranium hexafluoride 235, will effuse a little bit faster. So you're not going to increase the concentration by a lot, but if you do this a number of times, then you can eventually separate the one isotope of uranium from the other. So this was used during the Manhattan Project to purify the uranium that they needed for the first atomic bomb.